Okay, embedded
Amma,
system applications and domain specific.
Amma,
So,
काय पडेल?
what is this embedded application and domain specific? Application and domain specific in the last class, as we discussed, the embedded system has its own characteristic. Like it is designed for a particular application, right? And once it has been designed, once it has been fixed, it can be used only for that application. One example has been explained here, example of a washing machine. I hope washing machine is nothing but a simple example of an embedded system. If you imagine the working principle of embedded system or the washing machine, basically there are two types of washing machine, right? One is a front load washing machine as well as the top load washing machine. So the working principle of this both the machines are different. Okay, you consider in both the machines there will be certain sensors, there will be certain actuators, right? There will be various different types of system, embedded systems, which will be all clubbed together and generate a particular application. That is what I told you in the last presentation, right? It is a distributed system. Whenever we say application specific task, or if we consider embedded system design, it will be a distributed system. That is nothing but different types of systems, different embedded systems will be connected together to form to give a particular application, right? So in this particular example, if we consider uh, what all things we may have certain sensors, actuators, control units, right? In order to control the programming of the washing machine and application specific user interfaces, like in some of the machines you have keypads, right? The display units will be there. All these other different types or different systems what you have in the uh, uh, washing machine, right? So if I consider the actuator part of the washing machine, actuator is nothing but what the action. In order to control the machine, some action should be taken. So what are the actuators present in the washing machine? If you imagine, it consists of a motor, right? A motorized agitator, a tub, right? That is a tumble tub. You can, if you imagine it, certain times it will be vibrated, it will be rotated, right? Next, you have water drawing pump. You require an input, water input so that water drawing pump is required. An inlet valve is required to control the flow of the water into the unit, right? The sensor part consists of a water temperature. This is initially it was an activator. Activator consists of a motor, a tub, a water inlet, a water pump input, all that. Sensors, if I consider sensor, what are the different things you require in order to control the rotation of a motor? If you have observed that, you can set a temperature, you can set the RPM, right? In a washing machine, if we again observe, there will be different categories like hard, real, soft, or like for a cloth of wool, one button will be there for cotton, sports, like there's some various will be there. That is nothing but whenever you press it, what happens, either the temperature on which that machine will operate, that will vary, as well as the time required to rotate the motor will vary, and also the RPM of the motor will vary, right? So that all that has to be set. So for that, some sensors are required initially. So sensor part consists of a water temperature sensor to monitor the temperature of the water in the tub, level sensors. Okay, these are different types of sensors. Next is one more important part. What we have is a controller part, right? I require a control unit. A controller part consists of a microcontroller or maybe a microprocessor based board with interfaces to the sensors and actuator. It is the one which control all these sensors as well as actuator. You need to program the sensor and actuator, and that programming will be loaded to that control board. It can be a microprocessor or it can be an controller, ARM controller. Okay. So basically, the sensor data is fed, as you know that whatever input, whatever input you give or data, it is basically fed it to the, it will be fed to the control unit, right? Control unit, it is already pre-programmed. Suppose say that if you observe the keypad here in this particular diagram, what we have in the keypad, we have a say start button, light, medium, heavy, like three different phases of washing, wash, soak, as well as rinse, right? Next, the time is there, 30 minutes, 1 hour, 2 hours. This is nothing but the input what we give, right, to the sensor. So suppose say that I press this light. So that has to be detected by the control unit. For light, what programming is done? Before loading the program to the control unit, the designer will load a program. What program they are going to load? Say for the light particular section, say RPM should be 1000 10,000 RPM, the temperature should be so, and this is the water level. All that will be pre-programmed. Whenever you press it, that program should be executed, right? For example, if I consider light, if I say 1000 RPM, so water should rotate in 1000 RPM, and say temperature is 40 degrees Celsius, the temperature will be set for 40 degrees Celsius, right? And if the time is for 30 minutes, it should rotate for 30 minutes. Automatically, it should be done because it is programmed. So whenever you press it, sensor detects your key press, and accordingly it executes that and controls the actuator. Which are the actuators? Actuators are nothing but this spinning tub, right? A motor here as well as a water inlet, right? Water inlet pipe, whatever is it, this one, right? All these are nothing but will be controlled, and a level sensor to detect the level of the water. So along with that, once it is done, once it is rotated, whatever, as you know, there are three different types, like wash. Whenever wash increases, water will be there continuously, the motor will rotate. At the same time, this bubbles, if you observe, it is nothing but the holes in the tub. If you exactly observe the washing machine, just try out after the class, just go check the inner tub of the washing machine. There will be in between, there will be holes, and that is nothing but for the movement for the outer water outlet. What during the washing process, whatever water is there after spinning, it will be sent out through that particular holes, and through the water outlet, it will be sent out. So washing process, once the washing process is complete, next is nothing but soap, and the last one is the rinse. And we have an option. Suppose say if you want only rinse or if you want only soap, if you press that particular button, accordingly it will execute. It will work, right? So, so basically, washing machine comes in two model, as I told you, top model or a front load model. Based on that, based on the alignment, based on that architecture, it will work accordingly. Okay. So, like this is what I told. This is an embedded system. We'll be programming it. The board, whatever is programmed, it is used only for the washing machine architecture. I cannot use that particular board to an oven or to some other machine. It cannot be used, right? It is nothing but application specific and domain specific. Okay, so this is the basic block diagram what we have for a washing machine. That is the control panel. We have level sensors. We have water inlet and inner outer tub for the rotation of the tub, as well as outer water inlet over here, and different keypads and the LED display in order to display how many times, how many time is left that will be displayed in this LED. So this is what all these are nothing but an embedded. See, water inlet, it has to be programmed. This is one of the embedded system. Level sensor, this is also one of the embedded system. Water outlet, inner tub, or if you consider this keypad, it is a part of an embedded system. Or if you consider this LED control, it is an embedded system. So all the systems are clubbed together to form a particular task. So we call this embedded system as a distributed system. So the first characteristic says that application specific, right? Application and domain specific. Next it is a distributed system, right? So the next application or the major application of embedded system is in automotive, right? Automotive, they're also domain specific. So for example, you consider the car, vehicle. They have a lot of embedded system in that particular car, starting from say the fan control of an AC. Next, engine control. Again, it is again through an embedded system, the turning on, turning off of an engine. Various instruments are there, like USB device or MP3 players, air conditioner, power steering, or airbag system, anti-braking system, right? Seat control. If the seat belt is not, or if you have not put the seat belt, an alarm will be given to the user, right? Or else the movement of a seat to a particular angle. Mirror control again it is an automated process. You can exactly set an angle and set it in one direction. It need not be a manual again. Next, power windows, like turning up down of a power windows, all that can be controlled. Suspension control, right? Wiper control, like a headlamp control, everything. So many things are being controlled now by embedded system. Okay, so if I consider a vehicle, so many devices should be controlled. So in order to control that, there are In order to communicate between the various devices, there are different types of bus available. We'll be studying this in the next coming modules also. But basically, if I consider automotive communication bus, here in inner working of automobiles, okay, it has been divided into two sections. As I told you, there are lot many applications in the automobiles. Basically, there are two different types, two different categories under this section. One is high-speed electronic control unit, what we call as a HECUs, and low speed electronic control unit. So this is based on the type of the application we are going to use. High speed electronic control unit in the sense the applications which basically it is with respect to the data rate or rate to transfer the data from or control signal from one point to other point. The applications which requires to be executed in the real time. Say for example anti-braking system, ABS system, or else airbag system, or else engine control system, right? All those are nothing but a real time. It has to be executed within the time interval, or it has to be serviced within the time interval, or else it will affect the environment, right? If airbag doesn't open when the collision occurs, then what is the use of having an airbag? Or if anti-braking system doesn't work when you apply a brake, at that instant if it doesn't work, what is the use of having an ABS? It has to be executed, it has to be very fast. So all such type of applications will be under high-speed electronic control unit. For this, very high-speed buses will be used, as well as the controller, which we are going to use, the what we call the processors or the controllers. It will be of high speed. Okay, it should execute a particular task within the time interval. Next type is low speed electronic control units. In low speed electronic control units, like say power window control, wiper control, or else fuel indicator, such type of applications, where or seat belt control, where say even though if the window doesn't move up or down at a particular time interval, it is okay, it doesn't affect your external, right? So such type of applications where low power, sorry, what is that? Execution time may cross the deadline, will fall under low speed electronic control unit. Okay. Uh, Next is so in order to achieve this, different communication buses are used. So basically, there are three types of buses mentioned. First one is control area network. We call it as CAN bus. Second one is local internet network. We call it as LIN. Or third one is media oriented system transport, that is MOST. So first one, if I consider CAN bus, control area network. CAN bus originally was proposed by Robert Bosch. Okay, it provides, it supports a medium speed, that is say up to 125 kbps. Okay, one from 125 kbps to a max of say 1 mbps data rate, data transfer can take place. CAN is nothing but an event driven protocol. We will be studying this particular protocol in detail later, but basically it is a event driven protocol interface. Okay, event driven protocol which supports for error handling in data transmit. It is generally employed in safety, like airbag system. So that is nothing but whenever event occurs, certain action need to be take place, where high speed data rate should be done, because immediate has to be detected and we need to respond. Or ABS system, which is nothing but event, pressing a brake is nothing but an event. So all this CAN bus, basically it is used whenever an event based embedded systems are used, or whenever an event has to be detected and then you are going to take an action. In such type of applications, CAN bus will be used. Okay, that is CAN. Next one is local internet interconnect network. In local interconnect network, it is like a single master, multiple slave. Okay, it is a configuration of master slave configuration. Single master will be used and multiple slaves we have, where are like up to 16 independent slaves can be connected to this particular master. Okay, basically this LIN is a low speed single wire communication. That's what I told you. This LIN can be used in low speed electronic control unit, where the execution may not be real time, may not be in the sense, occasional failure is okay. Okay, in such type of application, in low speed electronic circuit, this local internetwork bus will be used. So here we have a single wire communication follows the master communication. Master communicator triggers the other slaves. Okay, it is nothing but triggering technique is used to eliminate the possible bus arbitration problem. The master will control all the other slave devices. From the master itself, the data will be sent to various slave devices. So basically, this will be used in the applications like say mirror control, fan control, or seat positioning controllers, window control, or position control where response time is not a critical issue. Okay, the response time, the execution time where it is not a critical issue in such type of applications, LIN bus can be used. Where response is critical and if it is event based applications, then we have to go for CAN bus. Okay, the last one is based on the network, that is most media oriented system transport. Basically, this media oriented system transport is targeted for automotive audio video equipment interfacing audio or video equipment interface, like through audio you're going to control, or if you want to check the video, based on that you need to take some decisions. In such type of applications where you need to process a video, right? Say for example, reverse parking system. If you want to detect how many meters are there or what is the overall angle, in such type of application, this media oriented system transport will be used. It is this bus is multimedia fiber optic point-to-point network implementation in a star ring or a daisy chain topology. Okay, basically it uses fiber cables. Okay, uh, and this bus specification defines a physical layer as well as application layer, network layer, and media access control. So basically, like various devices. This is nothing but it forms like a network. Various other devices can be connected to this network, and we can control those particular devices through the voice messages or something like that. So this is nothing but the application of embedded system in the automotive domain. So basically, this automotive domain will be classified applications of automotive domain based on the time constraints. It will be classified into two sections. That is, one is high-speed electronic circuit control unit, and other one is low-speed control unit. And in order to have the data rates, or in order to transfer the data from one device to the other device, different types of buses will be used based on the applications you are going to select it. The basic bus where high time critical is required, or the applications where time critical time plays a very important role. Such type of applications will fall under CAN buses, that is control area network. Others where time is not an issue, and such type of can be applications can be implemented using LIN bus, that is local interconnect network. Okay. The last one is media oriented system transport, where the network will be used. So this is about the applications of embedded system. Next topic, it is with respect to the hardware software co-design. So what is this hardware software co-design? The name itself indicates hardware and software and co-design. Hardware software co-design as well as programming model. So if you consider designing an embedded system, if you consider an example, say user will give their specification, like this is what I want. They won't tell you which embedded system you have to use or which controller you have to use, which input output device you have to use. No one will tell you. They will just tell this is my requirement. Suppose say one user comes to you and says that I want like automatic room controller system. What he tells is I want to maintain the temperature of a room exactly at 24 degrees Celsius, not more than that or not less than that. Okay, this is what user gives you the specification. Now the designer, what the designer does is the requirement will be taken from the user. For that requirement, we plan to design. Is it correct? So here comes this hardware software design issues, right? What we have to do is, suppose say if we imagine that room control system, temperature control system. So we need to maintain 24 degrees Celsius. So it means that every now and then we are supposed to read the temperature. So we can imagine, right? We require a temperature sensor. We have to read the temperature. Input is reading a temperature. The temperature should be sent to the control unit. In the control unit, we need to program such a way that we need to check whether the input temperature is equal to 24 degrees Celsius, or whether it is greater than 24 degrees Celsius, or whether it is less than 24 degrees Celsius, right? That control unit should check. If it is equal, fine, no problem, no action to be taken, right? If it is greater than 24 degrees Celsius, what we need to do? Either increase the AC, right? If it is less than 25 degrees, 24 degrees Celsius, what we are supposed to do? Either we need to turn off an AC for some time, right? That is nothing but action. We need to decide the action. Is it correct? So once requirement is given, next you will analyze that requirement. You will identify which are the hardware required, as well as you will identify which are the control units required, as well as you will identify what is the firmware, the software required in order to program it, right? And then in traditional approach, if we consider the traditional embedded system developed approach, this design, that is hardware requirement as well as software requirement, was completely two different tasks. There was no relation at all between two independent tasks. Okay, there was no relation at all. So, right, so in this earlier device, the hardware partitioning is done at early stage. That is, engineers from the software group take care of the software architecture development, and the implementation and engineers from the hardware group are responsible for building the hardware required for the product. It is true, this design was totally a separate process. Okay, they completely do their hardware, engineers do their design separately, software will do their design separately. They will check it, and after everything, all the process is complete, then they will club it. Okay, this there was less interaction, or we can say no interaction at all between the software design as well as the hardware design process. Okay, uh, so this design is to occur serially or parallelly. Once the hardware and software was ready, then integration was performed. Now again, saying this, a lot of time constraints will be involved. A lot time is required to design it, because initially hardware will be designed separately, software will be designed. Again, testing of the hardware will take place separately. Software testing will take place separately. Then again, you integrate it. After integration, again we are supposed to test it. If again the result goes wrong after integration, again it will be sent to the hardware, again the software, again the same process should continue. Right. So basically, it requires more time. So in order to avoid it, this concept, that is hardware software co-design approach, was introduced. In this particular technique, the product requirements captured from the customer are converted into the system level need. Okay, initially whatever requirement was received from the customer or the users were converted into the system level needs or processing requirements, rather than partitioning them into either hardware or software. You have a requirement. Okay, that requirement will be formed to a system level, in the sense like a form of a block diagram or a particular form of a flowchart. It will be converted. There we will not divide it based on the hardware. What is the hardware required? What is the software required? No, this is not done initially. A system level design will be done as the first step. Next, the system level processing requirements, whatever system level requirements we have done, the designer will do that. Then it is transferred into the functions. Okay, in the system level, I will get different steps. Say, for example, if I assume the same example, like maintaining a room temperature, it will be defined. First, the system requirement is like I'll have a box, I'll have a block of diagram, block in the system level will be there, system level diagram will be there, where the input for that is the temperature, right? In the internal block, I'm not worried now. Output is like maybe I will have two different output. One is to turn the increase the AC on or reduce the AC or turn off the AC. Like these are the things. So one system level is done. Next we go for functional design. In the sense your system level design will be divided into different functions. Remember, not again hardware or a software. Different functions it will be designed. Functions in the sense the first function, reading a temperature, it is one function. Second function, processing the temperature, checking whether it is equal, greater or less. If it is equal, what is that? If it is greater, what is that? If it is less, what is it? There is a third function, right? Is nothing but control. So design will be divided into various functions. That is the second step. After that, the architecture design flows the system design. Next, you will have an overall architecture for the system, like reading a temperature. That flow will be maintained. Okay, the partition of system level processing requirement in hardware and software take place during this during the architecture design. Exactly, I'll come to know what are the different hardwares I'm having, what are the different softwares we are supposed to use, and during this phase we will decide what are the hardwares and what are the softwares. This is not initial. In the earlier technique, that is traditional technique, at the requirement, once you get the requirement, there itself the partitioning was done. Here it is not done. After system level design, we'll have an architecture and then the partitioning is done. Each system level processing requirement is mapped as either hardware or the software requirement. Right? After in the system level, what we have done is we have define the entire system level design into various functions. Now what I can do is that functions can be mapped. Say reading a temperature, whether it can be implemented to the hardware through an hardware software, you require programming for that, right? That mapping should be there. Functions will be mapped either it is an hardware or the software. Okay. Next, that is at the architecture level. So the partitioning is performed based on the hardware software trade-offs. Okay. A certain trade-offs will be there based on that this partitioning will be done. So next, the fundamental issues in hardware software co-design approach. There are various issues involved whenever all this process will take place. That is hardware software co-design. First issue, this is very important topic. Fundamental issues involved in hardware and software code. I hope you have understood what is hardware software co-design. Next, when we go for this hardware software co-design, what are the issues involved? Okay. First one, is the model captures and describes, sorry, model selection. Okay, the first technique, it is nothing but a model selection. What is this model selection? Okay, a model is nothing but we need to, whatever requirements we have done, as we have seen in the in the previous slide, it is based on the requirement given by the user, the system requirements or what we call the functional requirements will be designed, right? That is nothing but say here the product requirements captured from the customer are converted into system level needs. Okay, so in order to convert that into system level needs, we need to represent that in the form of function. Those functions should be represented in the form of a model. Okay, so there are different types of models available, right? There are different varieties of models available in order to represent these functions. So which are the models available, or what are the different techniques available? That is nothing but a model captures and describes the system characteristics. When I represent it in the form of a model, it captures and it gives me the information of system characteristics. So a model is nothing but a formal system consisting of objects and composition rules. It is nothing but it is set of a rules. Say for example, if you consider a flow chart, you might have studied different types of models like representing in the form of a flow chart or representing in a form of say what is that FSM model, finite state machine model, right? There are different techniques involved. We will study the different models in the next class. There are different models available. So basically, if I consider the finite state machine model, what information it will give you? It will give me what is the present state. If this is the input, what will be the next state? If this is the input, what is the previous state? All that information, all the requirements of that particular architect or particular design will be given in the model. So basically, model is nothing but a formal system consisting of objects and composition rules. Everything will be mentioned. We need to design it, we need to write it. So it is hard to make a decision on which model should be followed in a particular system. There are different types of model available. So the designer should decide which model you are going to, either the flowchart you are going to use, either the finite state machine diagram you are going to use, or which are the different models. There are different types. We will go through it. So that is the first step. Selection of the model is nothing but one of the issue here. So most often a designer switch between a variety of model from the requirement specification to the implementation during this phase. Initially, the first phase is requirement. User will give the requirement. Next, you will design it. Right. After that, designing process is the next. Nothing but the implementation. At this, during this design process, it may happen such a way that that this model selection, so the models whatever we have designed, it may vary during this design process. It may vary. So it is one of the biggest issue when you design any system, selecting a model. Okay, so the objectives vary in each phase. As you design, you come to know the objective will also vary, or the different inputs or the different rules may vary. So whenever the rules vary during the design process, again you have to change this model, right? So it is one of the issues in hardware software co-design. Okay, the next issue is architecture selection. Okay, second issue, architecture selection. Architect selection. In the design process, as we mentioned, first you'll have the requirement, next you'll have a design, a system level design. Next, based on the system level, you will have different functions, and those functions will be represented in the form of an architecture. So the question arises on which is the different architectures we have and how we are going to select that architecture, right? So different architectures available. A model only captures the system characteristics and does not provide the information on how the system can be manufactured. The previous one, model selection, will give you the set of rules. It will tell which are the inputs and which are the outputs. It doesn't give you any information how we are going to design, right? Whereas architecture specifies how the system is going to implement in terms of the number and the types of different components and the interconnections among them, right? It exactly gives the informations, exactly how many components are available, how many components are required, what are the input, what are the output, how many ports are required, everything information we will get through the architecture only. So the model will get only the set of rules, okay? Set of rules or set of inputs, how it behaves, that information will be given through the model. But whereas in the architectural development, we will get the exact information of the hardware, the software, different types of numbers or different types of hardware involved. Okay, so what is this architect? Different types of architectures will be there, like controller architecture, which type of controller you're going to use. In that, you have studied, right? We have RISC machine, we have CISC machine, reduced instruction set, complex instruction set, and Verilog instruction word computing, single instruction, multiple data, multiple instruction, single data. So like this, various architectures will be there. So selecting an architecture is one of the issue in hardware as well as the software code design. Okay, so the next issue is with respect to the language selection. Again, once you have done, we have designed with architecture, we'll just go through the issues. Now later we will go through different how it is in different models available, different architectures available. We will go through in the next coming classes. Okay, so selection of a model, first issue, selection of an architecture, second issue, third issue is selection of a language. As you are aware that there are different types of languages available in order to write a program. It can be you can write a program in assembly level language, right? You can write a program in high level language. It is nothing but a programming language captures a computational model and maps it into the architecture. Whatever architecture you have to design, if your architecture should work, there should be some computation, there should be some program, right? So we need to write that. That is nothing but programming model, programming language. A model can be captured using multiple programming languages, like it can be C, it can be C++, C Sharp, Java, different types, as well as we have hardware languages like VSDL, embedded C, system C, Verilog, etc. for hardware implementation. So big challenge arises in selecting the languages, in which language you are going to code. Okay, certain languages are good in capturing certain computational model. For example, C++ is good candidate for capturing an object-oriented model. Okay, so only the prerequisite in selecting the program language for capturing model is that the language should capture the model easily. It should execute the model easily. If there are any updations or the changes required, it has to be done easily. So this is also one of the big challenge, selection of a language. The next challenge is partitioning of a system requirement into hardware and software. Right? Once this is done, this is also an important character. We need to partition it. Certain functions or certain architectures, whatever you have designed, whether it can be implemented only in hardware or software. So partition also plays a very important role. Implementation aspect of the system level requirement. It may be possible to implement the system requirements in either hardware or in the software. So we need to decide it. So various hardware software trade-offs like performance, reusability, effort, etc. are used for making the decision on the hardware. Okay, based on different trade-offs, we are going to select. We are going to select whether that particular system can be implemented using hardware or whether it can be implemented using software. So these are nothing but various challenges involved in selecting the hardware software code design. That is model selection, architecture selection, language selection, partition, system requirement into hardware and software.